All right, so today I'll be talking about Specter. And I've given a few talks on Specter. And the approach I've taken before is to just give like a grand tour of all of the features of Specter and show lots of examples of the kinds of things you can do with it and show the performance and all of that. And I found that actually people find it to be a very intuitive abstraction, and people don't have trouble grasping the examples. But something I've begun to realize is it's hard for people to grasp like the broader significance of Specter and how it can affect how you approach everyday programming and change how you think about everyday programming. And it's kind of like when you first learn recursion. Like, I started programming when I was 10 years old, and I don't think I learned recursion until I got to college. And it never got in my way. For me, programming back then was just a hobby, and I would make games and stuff like that, and I was always able to make the things I wanted to make. And then you learn recursion, you see it the first time, and okay, a function's calling itself. And then there's this like light bulb moment you need to have before you are able to really understand that and make it part of your lexicon for how you approach programming. And then like now for me, many years afterwards, it's just inconceivable to think of programming without recursion. And so Specter is kind of like that, where you need that light bulb moment. Except the difference is that with recursion, recursion is something that you use once in a while. Like I certainly don't use it in every function I write, and oftentimes I'll go days or weeks without using recursion. Specter is about supercharging your ability to use data structures and structure your data and query and manipulate it. That's an everyday, every hour programming task. So even shifting your perspective a little bit on that and having more ways to approach these problems has a huge, huge effect. And that has certainly been my experience with Specter as I've built it and also learned from it. So where I want to start off with is with kind of a mundane Clojure example, because I think this really illustrates a lot of that mental shift that you need to have to really benefit from something like Specter. And so the example is you have a map. So here it's just a map with keys to numbers, and you want to increment all the values in the map. So one good way to do this, just writing Clojure straight up, is you take your map and then you do the map operation on it. And so that will map over every key value pair in the map. And then for every key value pair, you return a new key value pair with the same key, but the incremented value. But of course, the output of the map operation is going to be a lazy sequence of these new key value pairs. So then you pipe it into this call right here to create a new map with the updated results. Okay, so this works, and then you might find yourself doing variations on this many times, where you want to run some function on every value of a map. And of course, we're good programmers, so we extract new functions when we're using common functionality. So then you write something like this MapValis function, which is kind of like a normal map, except it will run on these nested values in the hash map. And this is just the exact same code, except now we include the function parameter here. So you can see if when I run both of these both give the same results. All right, and I have it set up here so that in my examples, it'll print the input and also the output, so you can see how things change. Okay, so I've been programming Clojure very heavily for more than 5 years, like done a lot of projects, did a startup with it, and in every project I've ever done, I have needed this MapValis function in my project. It comes up all the time. It's a common use case. And when I look at other people's code, I actually see people with the exact same function in their code. And I actually was curious, so I went on GitHub and I did a search for defen MapValis. And I got 28 pages of results. And remember, this is only people who happen to have named it exactly the same way I happen to name it. And for the most part, people implement different ways, but sometimes the code is like literally identical to what I wrote. So I thought that was kind of interesting. Now, the thing about the MapValis function is it is not a good function. And I would actually say it's a terrible function because it purports to do something, the MapValis function. If you actually look at what it's doing, you want to, the only thing you care about when you use the MapValis function is running that function on individual values. Everything else the MapValis function does is about reconstructing the data structure, because it's an immutable transformation, so that it's the same as the original data structure, but only with those values changed. Right? So examples of that are like making sure you have the exact same key used here, doing this into call so that we get a map as the result. So really the MapValis function is about that reconstruction process and making sure your changes only affect what you intended to change. And the problem is MapValis is not composable. It only works for this specific use case where you have a map as your top-level data structure, and you want to change only the values in that map. Now, if you nest the data structure more, then you're back to square one, back to where you were with having this burden of having to reconstruct what you didn't change. So let me show some examples of that. Let's say you have a list of maps, and you want to increment all the values in those nested maps. So to do that in Clojure directly, you run the map function, and then you need a nested function which calls MapValis on those nested maps. Right? And you can see that works. So this doesn't seem so bad, but let's look at a vector of maps. So in this case, the code is almost the same, except in order to make sure we get a vector back and not a list back, you need to make sure to do the mapv call. The burden is always on you when you do these nested transformations to make sure that you don't change anything besides what you intended to change. And that requires a lot of care and precision. And in my 5 years of programming Clojure without Specter, I had to debug so many bugs caused because I made some little mistake in something like this. And it just gets so much worse the more complicated your data structures get. So here we have a map of vectors of maps, and we want to increment all the values in those nested maps. And this code is basically unreadable. You have MapValis to anonymous function to MapV to anonymous function to MapValis again. There's no way to look at that function and understand what it's doing. And that's a really big problem when you're working on a big project and you need to be able to go back and understand what the hell you wrote before. Okay, that code does work, though. So I kind of just lived with this. I think pretty much all of us kind of just live with this burden and this constant annoyance with programming Clojure. And I lived with this for a long time, and then I got to what I've been working on for the past few years. And what I've been doing is just so hard, and the project is so crazy large in scope that early on I realized that this just was not going to cut it anymore. When you work on a really big project, you need to be flexible. You need to be able to change and adapt and go back and understand the code you wrote. And I do a lot of stuff with directed acyclic graphs. And I have stuff where I have a directed acyclic graph, and then a node in my graph has embedded within it another directed acyclic graph. And I have this recursive structure. And the nodes are different record types, and the different record types have all sorts of structures, sometimes with nested records. And so if I want to change one value deeply nested within these graphs, and I can't just do the logic to change the value, but need to figure out how to reconstruct this really complicated structure, that's crazy. It's just not doable. So I actually considered, just because of this problem, using mutable data structures. No, because with a mutable data structure, you don't have to worry about the unchanged parts because you only change what you want, right? But fortunately, had Rich Hickey in my ear, easy doesn't mean simple, easy doesn't mean simple. And so that lasted lasted for 5 minutes, and then I, got my sanity back. But it just shows you how big of a problem this is. So basically, I just said, this is bullshit. And I probably dropped a couple F-bombs too. And And that's how Specter was born, out of total necessity. By the way, I'm pretty sure that like 99% of the like really useful things made in the world started off with someone saying, "This is bullshit." And there's probably like this like linear graph you can make between how useful the thing is and how many F-bombs were dropped when the thing was created. Like I can't even imagine like when Rich Hickey was inspired to make Clojure, he was probably working on some like Java, like debugging some issue with mutability. I bet you he dropped like 1,000 F-bombs right before he made Clojure. All right, anyway, so let's get back to Specter. Okay, so all right, so let's go back to MapValis and let's see how to do the equivalent like functionality, this idea of transforming the values in a map using the Specter approach. Okay, so here, this code here will increment all the values in the map, just like we were doing before. And the way it works is we say transform, and then we give it what's called a path, which literally just says how do we navigate to the values that we want to manipulate. So here we say navigate first all, so that navigates to all the key value pairs in the map. And then we navigate to the last value in the key value pairs, which will be the value. All right, so that gets us where we want to be. So then we say we want to run the inc function on every value, and then we give it our input map. And you can see when I run this, it works just like before. So there's like a big difference here. Like we tell it how to navigate to where we want to go, and then it handles all the work of reconstructing the rest of the data structure, the parts that we didn't change. That's all internalized in that navigation path. Now, if you find yourself doing this a lot, just going on the values of a map, you can factor out all last into something reusable. So here I say define MapValis as the composition of all and last. So comppath is a Specter function. And now if we want to do the exact same thing, but with our new higher level navigator, we just say transform MapValis, and this does the exact same thing as before. So this MapValis object here is the rough equivalent of the MapValis function we had before. But unlike that function, this is a great abstraction because it's composable. And you can use this within nested data structures just as easily as you can use it on a top-level data structure. So let me show some examples of that. So let's say you want to transform a list of maps like we had before. So here you would say transform all, so navigate to every map in the sequence, and then transform the MapValis. And we do that on the list, and you can see list in, list out with the transformations. Okay, so now let's do it on a vector of maps, and the code is identical because all recognizes the type that it's going over and makes sure to maintain that type. Okay, so vector in, vector out. Okay, now let's say you have a map of maps, so nested maps. So in this case, the navigation is navigate to MapValis and then to the values of those nested maps. And so here we have these doubly nested maps. And when I run the transformation, you can see that all the values got incremented appropriately. So now let's do that one that was absolutely disgusting with manual Clojure code, which was a map of vector of maps. In Specter, it's super easy. Transform MapValis, so that gets us to the vectors. Then for every map in the vectors, do MapValis again, and no problem, easy. Okay, so what's happening here is actually really profound. And what's happened here is that we've disassociated how we want to get to what we want to manipulate from the effect we want to have to what we want to manipulate. We've turned navigation into its own independent abstraction, something that's not tied into the particulars of a specific function, like how MapValis works. And what this enables is, now that navigation is its own abstraction, that can be manipulated and composed just like any other abstraction. And that's what enables this, what I think is pretty beautiful code. You've probably heard the saying, like, I'm sure everyone's heard this saying, like, because it's like part of the philosophy of Clojure. like better 100 functions operate on one data structure than 10 functions each on 10 data structures, right? I think we're all on board with that. So I would counter and say much better than that is a handful of navigators that compose to your specific transformations. Much better, because navigators, each new navigator you add, you have this like combinatorial explosion of things you can do. And instead of just having functions that only operate on that data structure if you have it right there at that point, which means if you have to work on that data structure nested, you need some anonymous functions to do it. With navigators, you can just, it's easy. It doesn't matter where it is. You just navigate to it, and you can do your work. Okay, so I want to show one more, also seemingly mundane example. Again, just to shift your perspective on how you think about certain kinds of programming tasks. So in this example, we'll work with a map of sets. And the operation we want to do is just to add a value to one of the nested sets. So here's the Clojure code for doing it. So let's say we want to add the value 1 to the set for the A key. So you'd say update data, update the A key, and then for the nested set, if there's a value there, then conj the value into the set. If there isn't, then just create a new set with the value in it. So you have to specially handle the nil case. And so I run this, and yeah, it works. Okay, so let's see a variety of ways to do this with Specter. And so the first approach is to just navigate to the set and then run a transformation function on the set. So transform A, and then here's our function, which takes in the set as input. And this actually is exactly the same as what we did before. So there's no improvement here by just navigating to the set and then transforming it. But you can see we get the same results. Okay, so let's take a different approach, and let's try to take some of that logic in this update function and express it as navigation. Okay, so here's one way to do it. So we'll say transform, and we'll navigate to the value for A. And then Specter has this nil to set navigation. Actually, this is built on top of something called nil to value, which you can parameterize with the value to replace if it's nil. But in this case, this is saying if we navigate to nil, instead navigate to the empty set. Otherwise, just stay navigated where you were. So it's reframing what to do when the value is not in the map in terms of a navigation. And like we're not navigating to like a nested data structure, but this can still be expressed in terms of navigation. Navigation is not just about literally nested like a list inside of a map. And now in our function, this is guaranteed to be a proper set, so to do the operation, you just conj the element into the set. Okay, but this I actually think is not the best approach. Okay, so here's another approach. So the idea here, okay, so it might take a second to wrap your head around this. What we'll do is we'll, again, navigate to the value for A. And now what we'll navigate to. Okay, so here, okay, so a set, you take a set of values. And it's a set, right? It doesn't seem like, I mean, there's just values. There's no nested data structures within it, right? So like, what do you navigate to within it? Well, I would say actually a set naturally contains tons of nested data structures, because a set can be expressed as the union of any of the subsets within it, including the empty set, right? So here, what we do here is we navigate to the empty subset of the set we're looking at. And now whatever we do to that empty subset will replace that empty subset within the larger set and basically just union those values back into the original set. So we can express adding to a set as replacing, navigating to the empty subset within it and replacing it. Okay, I hope that makes sense. And so here what we do is we navigate to the empty subset, and then our function doesn't care about the input because it's going to be the empty subset, and we just return the set of 1 to replace that empty subset with. Right? And you can actually make this a little bit more concise. This is a fairly common pattern where how you replace the values you navigate to doesn't actually depend on the value there, where you're just ignoring the argument. So there's this setVal function in Specter, which just wraps transform. So here we just say setVal, the empty subset at A, to the set of 1 on data. Okay? And we get the same thing that we've been getting. Now, is this like unequivocally better to what we were doing before? I think you can debate it. But my point here is that it's a different way of thinking about like something you've done a million times before. And I personally think this is better. That's my opinion. But it just enables you to approach things in different ways and increases your toolbox. Okay. So this idea of navigating to like the inherent substructure within a data structure, so you can do that with sets. I think it's even more apparent with sequences because there's so many ways to define a substructure of a sequence. So I just want to like go through a bunch of examples here. So here, what we're going to do here is we're going to navigate to the subsequence from indices 4 through 9 and replace that subsequence with the sequence hello world. So we're replacing a sequence of length 5 with a sequence of length 2, and here's what we operate on. And you can see when I run that, okay, so that big chunk in the middle of the sequence got replaced with this subsequence. Okay, so here's an example, same thing, but instead of just replacing it, we're going to run a function in the subsequence to reverse it. And so this reverses all the values in the middle of the sequence. Okay? Super easy, right? Not fun to do this manually. And because, like, keep harping on this point, why navigators are so awesome is because they're composable. So everything I'm showing you composes with everything else. So here, let's compose sRange with some other navigators. So this right here navigates to the subsequence between 4 and 9, then looks at every value in that subsequence. And then when you use a function in a navigator, just like a regular Clojure function, it acts as a filter. So it only stays navigated if that function returns true. So this has the effect of multiplying by 100 every even number in that subsequence. Okay? And you can see that works. So another way to look at navigating to the substructure of a sequence is to navigate to a filtered view of that sequence. So what I do here is I say transform filter even. So this actually navigates to a new sequence which only contains the even values of the original sequence. And the key thing is that you're navigating to the sequence, not to the individual even elements. So this is going to reverse the positions of all the even numbers within that larger sequence. Okay? And you can see all the odd numbers stay in the same place, all the even numbers flip positions. And so this gets cool when you take advantage of composability. So here, this next one reverses the positions of the even numbers, but only within the subsequence from indices 4 to 13. Okay, and there you have it right there. Okay, so far I've only been showing transformations, because that's like the really hard use case. But this idea of navigating works just as well for querying. So just a couple quick examples of it. This next example selects all the even numbers for the A key out of a sequence of maps. So all A even. Okay? So from that sequence, it extracts the values 2 and 4. Okay? And this next one here selects all the even numbers in the subsequence from indices 4 through 9. So similar path to what we used before, but now we're retrieving the results as a sequence instead of manipulating them. Okay, so all right. So now for my next example, I feel like I'm a magician. Like for my next trick, all right. This next example, I want to show but once you have navigation as its own abstraction, you can do some really interesting things when you do higher order things on top of paths as objects. And so this will demonstrate that. So here we're going to use this or do manipulations of this world data structure where it has 2 keys, so people and bank. People is just a list of maps which has the name of the person and the amount of money they have, and then the bank has a certain amount of funds. And what we want to do is write a function to transfer money from a user to the bank. Okay, so here's how you do it in Clojure manually. Yeah. All right, so first you have to actually retrieve the amount of funds that person has. So you can go into the people field, do a scan and filter to find that person, grab the money field. If the amount of funds they have is less than the transfer amount, you throw an exception. If not, then you can actually do the update. So you need to update both the person and the bank. Then you do the exact same thing you did before, which is navigate to the person, but now you have to do the reconstruction logic as you go. And then once you get there, like deeply nested in here, you finally actually take away their money. There's lots of reconstruction logic happening. And then to actually take it from the bank, well, Clojure thankfully has one operation for doing nested, one function for doing nested operations, but it only works on nested associative structures. So update in makes it far easier to actually add that amount to the bank. Okay, so you have this like mess of a function to do this. All right, so let's do this with Specter. And with Specter, I'm not going to do it directly. I'm going to do something a little bit different. And what I'm going to do is implement this function called transfer, which is a far more general function. And then we'll use transfer to do our specific operation. And cognitively, this is just way easier than like this mess up here. And so this transfer function takes in as input the world data structure, and it takes in as input two paths, a path to everyone to take money from, and then a path for everyone to give money to, and then it takes in an amount. So what this does is a fixed many-to-many transfer between any sets of entities. So the idea is if you select 3 people to give $50 to 2 people, each of those 2 people will receive $150, and each of the givers will give $100. Okay? All right, so the way this works is first, let's actually figure out how much money the givers and receivers currently have. So we just call Specter select from path world. So that gives us a sequence of their monetary amounts. And for the receivers, select to path world. So now we know how much each of the receivers has. And then we calculate the total amount every receiver will receive is the amount multiplied by the number of givers, and a similar thing for total give. All right, so if every giver has at least that amount of money, then we do our transformations. So we transform the from path, which is the givers, and we subtract out total give, and then we transform the to path and give them total receive. That's it. There's not really any nested stuff happening. Like, this is really easy to read. So another really cool property of this function, besides just how generic it is and how elegant it is, it's also completely agnostic to what the world data structure is. It's not specific to the example I showed you. It can work on any way you structure the world data structure, because all the details of where the money amounts are stored are completely encapsulated in the paths that you give as input. So this is like super general. You can use this on anything. This is just a generic fixed many-to-many transfer for anything. And now to do our specific operation, we'll first define a function which returns a path to a specific user. And so to do that, we navigate to the people field, and then we express the scan and filter via navigation. So navigate to every person and only keep the users where the name is equal to the name we're looking for. And then user to bank is just going to be transfer on the world, and the path is navigate to the user and then navigate to their money field, and then transfer to the bank's funds. That's it. So now if we actually run this, you can see that here I transferred $10 from John Smith to the bank, and you can see John Smith has $10 less and the bank has $10 more. Now, what makes this powerful is now we can use this transfer function to do all sorts of operations, like very, very easily. So here's a function that transfers $1 from every person and gives it to the bank. So transfer from everyone's money to the bank $1. We run that, and you can see that it works. If you want to do the opposite, or have the bank give $1 to everyone, then you just reverse the order of the paths. And so that works. If you want the bank to give $5,000 to the first 3 members in the users list, so you transfer from the bank's funds, and then you select the subsequence of the first 3 people, and then you select all of their money fields, and you transfer $5,000. And you can see that that works perfectly. Okay. Now, one really important thing for Specter is that it's data structure agnostic. For Specter at its core is like really simple. It's just a protocol, which is the interface for how to implement a navigator, and then it provides efficient means to compose those together so that they can execute quickly. And then Specter kind of has like a batteries included set of navigators built on top of those core abstractions to do all the common things that you want to do with like maps and lists and vectors and sets and all the common things. But the important thing is it's completely extensible, and there's nothing in the core of Specter that's specific to any of these data structures. And this is really important because you're going to use your own data structures. Like I mentioned, I do a lot of stuff with graphs. So I have a whole set of navigators that I made for graphs. And if I have time, I'll show some of it towards the end. But this is really important. Like if you want to have this abstraction to supercharge your ability to do the things you do with data, it needs to be able to work with any data that you want to use. Now, the interface for a navigator, it's really simple, really generic. So you have a separate case for when you're doing querying and a separate case for when you're doing transforming. And the way these work is that the implementation of select, the query case, is parameterized with how to do the rest of the selection from the sub-value from this point. And then the transform is likewise parameterized with how to finish the transform from whatever sub-values are at this point. So I want to show a couple implementations of this. So the first is key path. So key path is a navigator, which is parameterized with a key to navigate by. So basically, this can navigate by any key and not just by keywords, like I've been showing. So the implementation is, for the select case, is we navigate to the sub-value, which is going to be the value for the key inside the data structure, and then you call next fun on that, because next fun completes the selection from the sub-values. Okay? For the transform case, well, we do something similar, except in this case, next fun does the transformation for the sub-values, and then this function is responsible for reconstructing that back into the original data structure. And in this case, it's very simple. You just associate that new value for the same key into the data structure. Okay, so subset, which I showed before, is a little bit slightly more complicated. So here we need to navigate to the subset and then complete the selection or the transformation from that point. So navigating to the subset, so you give it some subset to navigate to, but of course you can only navigate to the values that the set actually has. So the navigation in this case for selection is complete the selection from the intersection of the parameterized set and then the set that we're actually looking at. And for the transform case, again, we navigate to that sub-value, which will be the intersection. Then you transform that sub-value. And then to have the effect of replacing whatever the subset was in the original set, you have to remove the subset we navigated to and then add in the transform subset that the user did. Okay. Might not be like the easiest thing to grasp this, but like I recommend just like studying it and thinking about it. Okay. All right, so Specter is extensible. So you can use it for any data you have. For any of your navigation needs. Now, another really important thing you need from Specter is it needs to be really fast. Because like when you manipulate data and do stuff with data structures, like you do that also in performance-sensitive code. And for Specter to be a useful abstraction, it needs to be usable everywhere. Because you don't want to have to say, oh, I can use this awesome abstraction like under these conditions where I don't need performance. And then for all the stuff which is in like performance-sensitive code, you have this giant mess of nested functions and all of that. So that's been like a really core focus of the project. And I just want to demonstrate a little bit of that. So what the little micro benchmarks I'm going to do are all going to operate on this data structure. So it's just a nested map. And the reason I'm showing you this, this particular use case is because this is like the hardest case for Specter to make fast, because the actual navigation part is super fast. You're just like getting the values in a map and associating the values in a map. There's like nothing to it. And so what you see in the numbers will be the overhead that Specter adds to actually doing the navigation. And this will really emphasize that. OK. All right, I'm also going to compare Specter against different ways of doing it in Clojure. So the first one I'll do is using Clojure's get-in operation, which is one of the few operations Clojure actually has for doing stuff with nested data structures. And I'm going to run this function here a million times and see how long it takes. OK, so you can see it takes about 80 milliseconds. So now I'm going to do it with Specter. So in the Specter case, it's select the path ABC from the data. OK, so it took 4.5 seconds. So it's 600 times slower than the regular Clojure code. So obviously, this is not the end of the story. Now, the way Specter works is when it composes your path together, it actually does like just like really intense optimization, which clearly takes a while to do. And so that's why it takes 4.5. That's how long it takes to just compose that together a million times. And the way Specter is performant is that whenever you need it to be fast, like really fast, you can pre-compile the path and then just use the compiled path. So up here, I define compiled path as the composition of the navigators A, B, and C. And now if I do the benchmark with the compiled path instead of just the path like it is up there, OK, so you can see it takes about 60 milliseconds, which is faster, significantly faster than get-in. Now, Specter has a function called compiled select and compiled transform, which if you know you're going to receive a compiled path, you can use that. And that strips away some of the additional overhead. And now it takes 50 milliseconds, so like a lot faster than get-in. And just as a point of reference, let's actually just do this with like completely inline code, where we just take the data and go to A, go to B, go to C. And then at the end here, I wrap it in a vector because select returns a sequence, and I want to do a fair comparison. And so you see this takes like a little under 40 milliseconds. So Specter's like, it's in the ballpark of totally inline code. And it's faster than what Clojure already has. All right, story gets a lot better for updates. So here, let's increment the nested value. And here we'll use Clojure's updateIn function. OK, so this takes a little over a second. OK, so let's do it with transform without precompilation. And you're going to see this will take about over 4 seconds. So again, it's about the same amount of time because all the work is in compiling the paths. But now if we use the compiled path, now it takes about 180 milliseconds. So 5 to 6 times faster than updateIn. And if we use compiled transform, it's even faster. So just dramatically faster than updateIn. And just as a point of comparison, here I have this manual transform function, which just does the transformation via a series of nested updates. So that would be like the inline way of doing it. And that takes 150 milliseconds. So Specter is really, really fast. All right, let me show one more example. I'll try to get through it quickly. So this is actually a relatively new feature of Specter, which is recursive navigation. And so basically, this is like a real use case that I had to build for what I've been working on. And basically, I have, like I was saying, these DAGs, and some nodes can have DAGs within them. And the operation I need to do is I need to take nodes of a certain type, I call them marker nodes, and remove them from the graph, and take the children of those nodes and attach it to what the parent of those nodes were. So the transformation looks like this. Okay? It's a recursive transformation. So let me show you what the code looks like with Specter. OK, so first we're going to define a path that navigates to all the reachable graphs and subgraphs. And so what we do is we first declare that we're going to make a path called reachable graph. And we declare it separately from the implementation because it needs to refer to itself for the recursion. And so what we say is continue, then stay. So navigate to this path that we provide, and then after navigating there, navigate to yourself. So this is basically post-order traversal. And so this is going to say, how do we get to the subgraphs from this graph? So first we navigate over all the nodes in topological order. And the way this works is it navigates to these pairs of the graph and then the ID for that node. And we just navigate to them all in order. And then node will actually navigate to the value for that node at that point. If it's an instance of a subgraph node, so something that contains a subgraph, then we navigate to the nested graph field and then call reachable graph on that. So this reachable graph navigates to every graph reachable from that starting graph. Then to do that squashing operation that I showed, you say transform. So first navigate to every reachable graph. Then we do that top sort again. If the node is an instance of the marker node, then we have a function that takes in the pair of graph and node ID. And then I have this squash operation, which actually does removing the node and reattaching the edges. Went through that kind of fast. But I just kind of wanted to demonstrate like something really sophisticated that you can do with Specter. And honestly, this is like doesn't come close to some of the other stuff I'm doing. But recursive navigation, all sorts of cool stuff you can do with it. So this is where you get to when you kind of level up in your Specter ability. I think I'm out of time. But if you want to see like more like interesting like graph examples or sophisticated stuff, like feel free to stop me. And hope you guys make good use of Specter. Thank you.